Hello ROOTCON, what's going on? I'm Banana Man. I do red teaming and I do pen testing, but today I'm talking about game hacking. I'm presenting a few game hacks today, and I've created a blog post for each game that I've developed a cheat for, and you can read those blog posts at this URL. So that's me, 12 years old, wondering how all these aimbots and wall hacks and other fancy Counter-Strike cheats are working. And I've dug deeper into this topic and I'm presenting my research today. First, let's talk about motivation of game hacking and cheating in online games. Nowadays, there are tournaments where you can win lots of money, and as a cheater, you can get more money and potentially money more easily by buying a cheat that are based on subscription models. So, for example, you can buy a cheat today for €7 and it's valid for 7 days. And you can cheat however you like during those 7 days. It may be online or it may be at an on-site tournament. Cheat vendors claim that their hacks are undetected and that these hacks are humanized, which means that they mimic human behavior, for example, when aiming at an enemy or when performing other automated stuff. You're not allowed to attach a debugger to your cheat that you've just paid for, otherwise you may get banned from the cheat service. And these people also claim that they don't keep any logs, but please just trust us, our hacks are legit. So as you can see, cheats can be very sophisticated nowadays, and I've wanted to dive deeper into this topic, starting at the basics. First of all, what kind of cheat types exist? First, there's a wall hack, which lets you see enemies through walls. Another thing is an aimbot, which automatically aims at enemies, which can also be combined with a trigger bot, so it automatically pulls the trigger and you basically only have to run around on a map and the cheat does everything for you. Also, there are game-specific hacks. For example, for Counter-Strike, you can implement a no flash, which makes you immune to flashbang grenades that would otherwise block your view. And there are also crosshair hacks. If you're equipping a certain weapon in Counter-Strike, you don't have a crosshair anymore, which makes it hard to shoot enemies without using the scope. But a crosshair hack always enables this crosshair, so you don't have to scope and shoot enemies more quickly. There are various approaches for game hacking, two of them being internal and external. And you can distinguish those two by checking the approach that's used to manipulate the game. For internal hacks, you're creating a DLL that's getting injected into the game's process and it's working from within the game's memory space. It's usually started as a separate thread of a game. External hacks are using their own process and they're just reading and writing memory of another process from outside. Also, games can be instrumented using something like Frida, which I'm also going into a bit in this talk. There are a few tools that are required. For example, you need Visual Studio if you're writing your cheats in C++ like I do. Also, a debugger is required. I'm always using x64 debug. And you also need a disassembler or decompiler of your choice. And most importantly, you may need Cheat Engine. It's a tool that can be used to inspect and analyze a game's memory. It also includes a disassembler, it includes scripting support, and it runs on Windows and Linux. It has some handy features that are really important for game hacking. You can, for example, scan for known values. So suppose you're health in a game is 92, you can search the game's memory space for an integer of value 92, and you can check what reads or writes to this address. For example, to prevent decreasing your health, or you can also freeze values to prevent running out of ammunition. Here's a little demo I've created for a cheat engine. I'm running the cheat engine graphical interface on the bottom right, and on the top right there's the cheat engine server that's running on my Linux system. This cheat engine server is running natively, and the graphical interface, it was started using Wine. On the left you can see a short Python script that just prints YOLOCON each second. And my goal is to change this string while this script is running. So I've used cheat engine, as you can see, to attach to this Python process, and I'm now searching for a string with the value YOLOCON, and I found a few results. And what's now possible is that you can select each individual result of the search and change the value of it. And as you can see, changing a few values didn't cause any effect on the printed text, but on a third try, I've successfully changed this string value, which now makes the Python script print ROOTCON each time. So that's a very basic example of using cheat engine. First, I'm creating an internal hack for Windows-based games. I'm using two games for this, one of them being Star Wars Jedi Knight Jedi Academy, and the other one being Counter-Strike Go. The plan is to build a DLL loader, build a DLL that's being injected into the game, and implementing some hacks. This is an example of a very basic loader, which takes an existing DLL, loads it into the target process, and starts a remote thread in this game. First thing I'm doing is opening a process using its PID, and I'm storing the handle for this process in this variable. Next thing is I'm getting the address of the Windows API function load library A in the kernel 32 DLL, and I'm storing this address in this variable. Next, I'm allocating memory in the target process, for example, the game. I'm allocating max path bytes, and I'm making it readable and writable. Next, I'm writing into this allocated memory of the game's process, and I'm writing the contents of a DLL path into this. So the absolute path to a DLL that's going to be injected will reside in this memory space. And the last thing to do is to create a remote thread in the game that's calling the load library A function with the argument allocated mem, which contains the path to the DLL. So this snippet forces the game to call load library A and make it load our DLL. And as soon as this DLL is getting loaded, the function DLL main is getting executed. And as soon as it's getting executed, you're running in the process of the game. For example, you can then spawn a message box to show that it's actually working. So at this point, creating game hacks is very game and game engine specific. It depends what you have to hook and what values you have to manipulate. For example, the Jedi Academy game uses the Quake 3 engine, and Counter-Strike Go uses Source engine. So your approach will differ when creating a wall hack, for example. The first thing I'm going to show is creating a few hacks for Jedi Academy, and the first thing being a wall hack. You have to know a few things about the Quake 3 game engine, and most importantly, some functionality is split into multiple mini VMs, and those VMs are implemented in own DLLs that are getting loaded at runtime. So for example, if a game wants to add an entity to the screen, for example, it's an enemy or it's a weapon or it's a thing you can pick up on the map, the main executable will call into this client game VM and request it to perform the actual heavy lifting. That's just how the engine architecture is built. And there's one important call when it comes to implementing a wall hack, and that's a call to add ref entity to scene. This call has to be intercepted, and I'll show you how in just a few slides. There's a function that's called CL cgame system calls, and it's implemented in the cgamex86 DLL file, which is being loaded and executed by the main executable called champ.exe. As soon as a game starts, the champ.exe process will load the cgamex86 DLL, and it will call getProcAddress for a specific function, and getProcAddress will then return this function address, which champ.exe now uses to perform the actual call. And the plan is to hook getProcAddress for the game and return an own address for a requested function. And in all other cases, we can just return the original address that's being requested. The specific function the main executable uses to call into this mini VM is called DLL entry. Calls into this DLL are being made as soon as an entity is being added to a frame, in case an entity moves, and in case game data is received from the server. So DLL entry is like an interface for the main executable to call into the client game VM, which actually performs the calls that are being requested. So the plan is to hook getProcAddress and manipulate the address returned for DLL entry. And at this point, we are taking control over the DLL entry point for this DLL, and we can intercept all calls with commands that are related to adding entities to the screen. In order to perform the actual hooking, I've used a hooking library for this. It's called mhook, and it's really simple. I'm just using the address of the original getProcAddress function, and I'm telling it to redirect all calls into my hook getProcAddress function, which I've implemented here. And as you can see, I am returning my own DLL entry function in case DLL entry is being requested. And in all other cases, I'm just returning the original function address that's being requested by the main executable. So as soon as I'm in control of the DLL entry point, I can check which command is getting requested by the main executable. In case it wants to add an entity to the screen, I'm getting the ref entity object from the first argument, and I'm just adding a single flag to the rendering effects. This flag, rf-defhack, is built into the Quake 3 engine, and it tells the game to display an enemy or an entity in general on top of walls, so you can actually see them no matter what's between you and an enemy. And that's basically the wall hack. So a helpful thing when implementing hacks like this is actually including the provided software development kit for this game, so you actually have access to all those structs and those flags, so you don't have to reverse engineer them yourself. So here's a demo of the wall hack. You can see the enemies through walls, and I've also added custom shaders to entities, which makes it easy to distinguish between enemies, dead players, or allies in a running game. The next thing I did was implementing an aimbot, and it locks the view at an enemy as soon as a designated aim key is being held. So you can hold the left control button, and as soon as you're looking at an enemy, the view gets locked on this enemy and you can just shoot, and the hack will perform all this aiming stuff for you. And there are a few requirements for this to work. First of all, you need to know what kind of enemies are present in the game, and you need to know their locations. And since I'm already in control over the DLL entry point and all calls that are being made into this DLL, I can just hook another command, just like in the wall hack, but for another call. And as I said, this DLL entry is also getting called in case game data is being received by the server. So I can just place a hook there and steal all the structures and memory contents that are coming from the server, and now I know which enemies are present in the game. So the few missing things are getting the actual enemy from a crosshair, calculating the correct angle to view at the enemy, and setting the angle programmatically. There's a structure in memory that's called client game, and I've got this structure from the C game hooks I've just talked about, and it contains a member that's called crosshair client number. So I'm getting this crosshair client number, and I'm comparing this number to the client number of every entity that's known to me and that's present in the game. And as soon as this number matches, I know that I found the correct entity to work with. So this has to be the enemy that I'm looking at currently. So now I'm ending up with 3D coordinates of my enemy, 3D coordinates of my local player, and I need to find a way to calculate the view angle, which is 2D. So it's like X and Y coordinates on my screen that have to adjust to view at this enemy. And this calculation and transformation is done with a world to screen function. It takes the 3D world coordinates, performs some calculation and projection, and it comes up with 2D screen coordinates that I can use in my aimbot. And there are standard world to screen functions that are ready to use. I found one for Quake 3 engine on the site called Guided Hacking. Since I don't have time to explain this in great detail, I'm going over it fairly quickly. What I did was creating a wrapper around this world to screen function that was provided by Guided Hacking, and I'm giving it the entity object of my enemy and a revdev t object, which contains information about my view, my field of view, and my screen width and all that stuff. I'm getting my enemy's position, and I'm just adding 30 to the C coordinate to make it automatically aim at the enemy's head instead of its chest. And now I'm only calling this world to screen function for my chest or now head value, which sets this screen vector, which I can now use to send input to the game. Now, why am I sending input to the game? There are many ways to set the camera angle programmatically. For example, in a few games, you can just write to a few specific memory addresses and the game will adjust its view based on these memory contents. But for this game, this won't work. So I had to actually emulate mouse movement for this to work. So I'm creating this input object and I'm setting the dx and dy values according to the values my world to screen function has calculated, and then I'm just sending this input to the game, and it now automatically aims at enemies as long as I'm holding my aim key. Next up, there's a thing in this game that's called force grip. It lets you grip an enemy and throw it into holes so they die. And I've wanted to create a cheat feature that automatically detects that you're being gripped and that tries to break the grip without you having to do anything. So the plan is to get the entity of the enemy that's attacking you, that's gripping your local player. Use the aimbot functionality that I've already implemented to look at this enemy and to execute a force throw which cancels the grip. And there's only a bit of code that has to be implemented for this. Each frame I'm checking if my local player is set and if I'm being force gripped currently, or if I'm being force crippled, so my local player can't move currently. If this is the case, I'm getting the client number of my current attacker, which is present in this data structure. I'm looping over all entities to check if the client number matches. And as soon as I'm getting the enemy's entity, I'm focusing the enemy's entity using the aimbot functionality I already have. And then I'm just executing a force throw. And just like I'm able to intercept calls into DLL entry for a few specific commands, I can just execute them myself. So I'm telling the game to execute a console command, which is called force throw, which is already implemented in the game. And it will just emulate me pressing the force throw button. And that's how it looks like in action. As soon as I'm being gripped, my player will focus the enemy and perform a force push, so the enemy is not able to move my player. Also, there's a thing in Star Wars that's called mind trick, and if an enemy mind tricks you, you are not able to see this enemy anymore for a few seconds. And there's also another force power that's called force C that lets you see invisible players. So what I did was I was checking if someone is mind tricking me or I'm enabling my hack manually. And I'm telling the game that I have force C activated. So it displays all invisible players, and this even works in case force is actually disabled on the server. I'm doing this by modifying my local player state, and there's a bit field that I can set using this command, and I'm telling it that I have force C activated currently. Similar to this, there are certain client-side settings that are considered as cheats. For example, R full bright can be used to disable all shadows on the map, which is obviously an advantage in a game. So if you're setting SV cheats to 1, you're telling your local game that the server actually allows cheats to be enabled, so you can use this forbidden setting. So now let's talk about a hack I've created for Counter-Strike Go. I've created a crosshair hack, which enables the crosshair even though it's disabled for a specific weapon. And for this, I'm hooking the DirectX, Direct3D, and Scene function. This function is being called as soon as a frame is ready to be presented on a screen. So it's ideal for hooking because it's executed after a scene has been created and is actually completed, and there won't be any more changes to it. So my plan was to create a DLL with an endscene hook function that acts like the original endscene function, but that contains my functionality. I'm then injecting this DLL into the game using the loader I've already presented. The function prototype for endScene is parameterless, but in case you're using it to perform hooking and game hacking, you have to keep in mind that there's an implicit this parameter that you have to implement. Otherwise, calls to your hook function may fail. So in order to set up the hook, you need to get the address of endScene in the game while the game is running. Also, you need a function that actually performs the hooking. Now, there are a few techniques to get the endScene function address at runtime. You can, for example, scan memory contents and perform pattern matching to find the start of this endScene function, but that's not a reliable way and it's by no means universal. But there's a technique that's called the pseudo-device technique, and I've read about this also on Guided Hacking, so credits to them. And it works by creating an own direct 3D device. And this object contains a vtable, which in turn contains the address of the endScene function. So I can just copy this function address, throw the dummy device away, and perform some hooking. In the source code of Direct3D, you can see that Direct3D device implements this interface, and at index 42 you can see that it contains the function for endScene, which is the vtable entry. So to implement this pseudo device technique, I'm creating a dummy device which acts like a Direct3D device, but the difference is that I'm not using it. I'm just instantiating the object. I'm doing some initialization using the create device call. And as a last thing, I'm performing a mem copy on this dummy device object, and I'm reading the contents into my own data structure. And lastly, I'm throwing the device away. Because I already have all this information I need, I can get the address of the original endScene function by reading this index of the Direct3D device vtable. So now the only thing that's actually missing is setting up hooking. So for this, I'm using the trampoline hooking method, and it looks like this. This is my original endScene function, and this is its prologue. I'm allocating some memory in the game's memory space, and I'm copying this function prologue into it. Next, I'm adding a jump instruction that jumps into endScene directly after the prologue, so into this location. And as a last thing, I'm setting up a jump instruction at the start of endScene that jumps into my hooking function. And what this does is, in case endScene gets called, it jumps to my hooking function, performs all this cool hacking stuff. It calls my function trampoline, which sets up the parameters and jumps into endScene again to perform the actual work that's done by endScene. The reason why I'm using a trampoline is that I would have an infinite loop otherwise. So in case endScene gets called, it jumps into my hooking function. This hooking function would then call endScene again, and it would jump to my hook function again, which is kind of pointless. So here's what it looks like in code. I have this hook function, which takes a function that's about to be hooked, and my function that is the replacement for it, and some other non-important parameters. I'm reading the prologue of the original function into this backup bytes data structure, which I'm using to perform unhooking afterwards. So I can restore the original prologue if I don't want to use the hack anymore. Next, I'm setting up my trampoline by calling virtual alloc, and I'm allocating some space that's executable and read-writable. Then I'm copying the prolog of my hooked function into my trampoline, and I'm done with the first step. Then the trampoline has to jump to a specific location in end scene. So I'm adding a relative jump instruction to this trampoline, and I'm adding the offset that the jump has to perform directly afterwards. So it's a valid jump instruction. And as a last step, the original end scene function has to be modified so it jumps into my end scene hook function. For this, I'm using virtual protect to make this memory segment writable. I'm calculating the offset for this relative jump instruction. I'm adding the relative jump instruction to the hooked function. And I'm using virtual protect again to restore the old protection values. And here's what it looks like in an assembly view. Here's the original end scene function with its prolog and the actual code. Next, here's the hooked end scene function, which contains a jump instruction into my DLL. Next, there are a few leftover trash bytes that are never going to be executed. And then there's the actual code for end scene. And lastly, here's my trampoline, which contains the copied prolog and a jump back into the original end scene. And you can see that it jumps right here where the valid and legitimate code of end scene starts. Here's a little proof of concept function for the end scene hook. I'm using it to just draw a small rectangle on a screen, and I'm using the trampoline to call the legitimate end scene function afterwards, so the game can continue as planned. Then you have to compile this DLL for x86 because CSGO is an x86 based game. And you have to add the DirectX software development kit to the linker libraries, so you actually have access to all the headers you're needing. A neat trick is to download the symbols for the Direct 3D DLL, so you can actually debug your stuff and check what's going on in end scene as soon as you're writing stuff and manipulating this function. And here's what it looks like in action. In the animation above, I don't have the hack activated, and on the animation below you can see my beautiful crosshair, and I'm now able to shoot people without using the scope. Okay, so now check out some external cheats. It works by reading and analyzing a game's memory from outside, and it works without code injection. I have implemented an aimbot and no flash for Counter-Strike Go, and you can also implement some more stuff. I've used Cheat Engine heavily to reverse engineer the structures of this game, and I've used it to perform some memory scans, just like the scan I've showed before. To make this analysis a bit easier, I've used the leaked game source code you can find on GitHub, and there's also existing cheat source code which you can use in case you're having any problems. The first thing I've needed was a reliable way to find the object of my local player in the game's memory. And for this, I've used Cheat Engine to scan for a known value like my health or my location. And I've performed some analysis and found a reliable way to find my player object using Cheat Engine. The important thing is that you need a static pointer to your local player in memory, because if you're restarting the game, your old pointer won't be valid anymore because the game and all shared objects are loaded at a different address. And I'm saying shared object because I'm implementing this hack for the Linux version of Counter-Strike Go. My approach to finding such a static pointer is finding various ways to find my player in memory and then keeping all the addresses I found in the game in the address list of Cheat Engine and restarting the game a few times. And some of these pointers remained valid, so I can use them to find my local player using a deterministic way. And I can actually hardcode this address in my hack, so I don't have to perform any scans in the hack itself, only for analysis purposes. But if you want to create an external hack yourself, you don't have to do this because there are tools like Haste Dumper, which can be used to perform a scan while the game is running, and it's printing a list of addresses you can use directly in your cheat. It does all the stuff by pattern matching known byte segments in the game's process memory. But of course, you have to run this every time an update is being applied to Counter-Strike Go, since these offsets may change. Also, some host structs or members may change, so there's a certain possibility that your hack may break if you're following this approach. So here's a little demo of me implementing a no-flash hack. As you can see, I was just flashbanged by a grenade. I only saw white contents on the screen. And now I'm using a flashbang and it's not doing anything to my view. And this works by constantly writing the value 0 to a member variable of my local player, which is like a very easy hack for this game. But you can also implement aimbots using external cheats, like I'm showing it in this animation. If you want to know more about external hacks on Linux for Counter-Strike Go, you can watch my talk from B-Sides Munich, which happened a few months ago. And I'll proceed with game hacking with Frida. This works by injecting JavaScript code and a JavaScript runtime into a game's process, so you can perform hooking and tracing. And this guy, Travis Ormandy, already implemented such a thing. He's developed an API for the game Simpsons Hit and Run, and he was able to spawn coins or control the player by using JavaScript code. So here's a little example he implemented. It's a function called kick, and it just simulates a key press, so the player performs a kick. He also implemented a function called step, which moves in the current direction. And the actual proof of concept he provided was finding objects around you and just kicking them and breaking them. So if you don't want to create a low-level hooking-based hack, you can also use Frida. It may be helpful for you. And now some last words about cheat detection. Some people say that anti-cheats are a joke, and specifically WAG, which is the anti-cheat for Counter-Strike Go. It uses signatures, just like your average antivirus engine, to find known hacks. And it also only detects a few specific kinds of hooks. So if you're performing hooking at the start of a function, like I've shown before, you may get flagged. So a solution is to hook mid-function instead of the beginning of a function. Also, don't use public code, write your own code, and you should be safe. But you can also use more fancy techniques like unhooking, polymorphism, and manual mapping. Now a few words about manual mapping. It's a fancy DLL injector which bypasses some checks that your average anti-cheat looks for. The goal is that your DLL doesn't show up in the loaded modules and that it also doesn't show up in the process environment block. And the general approach is to re-implement loaded library yourself so that the kernel isn't aware that the DLL has actually been loaded. And this works as follows. You're loading the raw DLL into your injector, and you're parsing the sections that this DLL contains, and you're mapping them into the game's process. Next, you're injecting a loader shellcode in the game's process, which performs a few things like relocating, fixing imports, TLS callbacks, and actually calling DLL main. So first of all, relocations. Each DLL has a base address that it wants to be mapped at, and if case this address isn't available, it has to be relocated to a different base address. And of course, in case a relocation takes place, global variables and addresses for call instructions have to be adjusted as well. So you have to perform these steps while relocating. Also, imports your injected DLL may require additional functions of other DLLs. So in order to fix imports, you have to load these DLLs yourself and setting the pointers and the DLL header accordingly. TLS callbacks are for thread local storage, and these callbacks are actually getting executed before your DLL entry point gets called. And each DLL contains a TLS table, and it contains information for these TLS callbacks, which you have to manually call. That's it. Thanks for having me. If you have any questions, you can ask right now, and you can also ask me on Twitter if you want to know anything more. And here are a few references you can check out. I really recommend reading some stuff on guided hacking, and for more questions, you can also check out my blog posts. Bye bye.